Amazing. So, off to our next speaker. Really excited to introduce our next speaker. He believes that making data and the processing of data easily accessible to non expert users is a great way to make the world a better place. He finished his PhD round tripping between the University of Wisconsin Madison and Stanford University and spent a year as a postdoc at Stanford. He contributed to research efforts that won the Sigmod Best Paper Award as well as the Research Highlight Award. Please welcome to the stage Assistant Professor at ETH Zürich, Zhang.
Should I start? Sorry. Okay, hi everyone. Thanks so much for the invitation. So I'm currently at ETH Zurich. Before that, I was a student with Chris and learned a huge amount of things from him. So today, I'm very happy to share with you essentially the thing that we have been working on over the last couple of years. Essentially, try to understand how can we build data systems to really help the DevOps process of data-centric AI systems. So over the years, we have been looking at how different users are building machine learning applications, and our research is actually governed by two observations. So the first observation is that over the years, we see the continued democratization of machine learning. Machine learning have been applied to more and more applications and have been developed by more and more people. So the consequence of that is if you look at the computer science and machine learning background from many of the users, so it's actually not as strong as a couple of years ago. So they start to have more and more domain experts who are really deep into domain science, start to build machine learning systems all by themselves. And in my opinion, that's really a good thing because we want machine learning application to be developed by people who really, really understand them. So on the other hand, we also see the increased complexity of building machine learning applications and also deploying machine learning applications. So on one hand, hardware are getting more and more heterogeneous, and so does data ecosystems. Data is kind of everywhere, and people start to train machine learning applications everywhere. And the machine learning technology has been rapidly advancing, and also there's also start to have regulations and requirements beyond getting some model simply have good accuracy. So if you look at these two trends and look at what we have today with all those users building complex machine learning applications with their current machine learning tools, right? I think it's fair to say that it has never been easier for someone to get some machine learning model out of today's AutoML tools. However, I think it's also fair to say that whether this model that they are getting is the right one or is a good one, it's getting harder and harder to answer. And also, if they are not good enough, how to systematically improve such a model is also getting harder and harder to answer. So essentially, over the last couple of years, one thing that we really try to understand is how to provide user a systematic step-by-step guideline for the development and the operational aspect of machine learning. If you remember the 5 tips from Andrew's talk just happened, right? So essentially our goal is really try to think about whether we can construct machine learning system and platform to really help our users to enforce those tips, even if they are not really the experts. So we don't know the answer, but this is what we have been working on over the last couple of years. So essentially, we try to define an end-to-end process to get the users through the development and operational journey of machine learning applications. This all start from the data and go through multiple stages, and we actually have some research projects for each of the stage. So first stage is about parsing and augmentation and data injection, and then it's go to another stage that we call feasibility study to really, before you run expensive machine tasks, right, we want to understand whether your data quality is actually good enough or not. And then it goes through the active kind of data cleaning and the data acquisition, right, to really try to improve the data artifact. And then it comes to the AutoML system, give you a stream of machine learning models. Here we also curious about how to do continuous degradation and continuous deliverable, like delivery of machine learning models, and how can we really continue to optimize its quality and conduct a kind of adaptation given the production data stream. So we have been looking at different stage in this picture, and we have two observations. So first observation is there are two different cycles in this large picture. So the first cycle is actually a data cycle. It's the continuous process of improving the data quality either by data cleaning or data acquisition. So the second cycle is actually the model cycle, where the model, where the AutoML system give you a stream of models, and then you try to continuous testing and adapt those models driven by your production data. So if you look at these two different cycles, you can see all of them are actually data-centric, but they are in different ways. So today, let me tell you a little bit about this small island, this kind of three different components. So I will tell you a little bit about what do we know over the last couple of years. And also, I will also tell you the things that we have no idea how to do. And also together with the things that we didn't even know that we don't know, right? So this comes to the components that we are here to actually ask for help from the community to help us to understand how to do this even better. Okay, so for each of these components, they are actually driven by some questions that we want to help our user to understand. So the first question is that if you have a data artifact, a training data, what is the best accuracy that any machine learning model can achieve on this piece of data? So we are curious about this question, not out of the blue, but actually motivated by a real story. So that is a couple years ago, one of my friends who is a biologist come to me with one data set. So essentially, he's curious about this. He say, okay, can you do some machine learning on this data set? The reason that he come to me is they have been trying to do AutoML on that data set for quite a long time. They try a whole bunch of things, but they cannot get the accuracy that they want. Well, man, we try to look at the data for a couple of days, and then we go back to him to say, okay, are you sure your data is actually correct? Because if you look at all those different examples, even though they have a very similar features, but they have very different label. So that actually triggers them to actually look at their data set. And after a couple of days, oops, it turns out all the labels are just pure noise. So this actually inspired our journey that we try to understand how can we prevent this from happening. And if you remember Andrew's first tip, right? So when the label Y is so inconsistent, can we build a system to help the user to detect that? So that actually goes back to our first realization that when you are talking about machine learning problems, often they are actually entangled from two parts. First one is the data problem, and second is the model problem. And somehow we need to help the user to provide the signal to actually tease them apart. So this is actually a problem that we have been working on for a while. We have a user, we have a data set, could have a whole bunch of problems. It could have missing value, could have noise, and then we have your machine learning technology. So these three different players interact in two ways. The user comes in with some expectation of what she thinks machine learning can do. For example, she thinks, I really want to get 90% accuracy on this piece of data. On the other hand, machine learning technology also comes in as a limitation. For example, there's no way you can get accuracy higher than 70% because of your data quality issues. One thing we want to understand is really try to check whether this expectation is smaller than the limitation of machine learning. Because if the answer is yes, the user better spend time to fix the data instead of firing up expensive AutoML runs. If the answer is no, maybe you should just do machine learning on this piece of data. So our goal is really try to understand how can we check this condition as fast as possible. So in the following, let me tell you a little bit about what we know, and also let me also tell you about things that we know that we don't know. Okay, so what do we know? One thing that we know is when training and testing data from same distribution, we actually have some idea about how to talk about this problem. So this goes back to a really traditional problem called the irreducible error, which essentially try to ask for what is the base error rate on this data set. So this is actually a very natural idea. So like assuming you have a two-dimensional feature space, right? They are kind of discrete feature space, right? So, and then if you look at this small bucket, assuming you have a lot of red labels and only a few green labels, right? You know, right? So if you're looking at this cell, right, you have to make the green many errors for this cell because even the best classifier can only make some deterministic prediction, which if you predict right, so this is actually optimal in this case, and then you take the integral of the whole space, that's give you the base error. So this is actually measures what the best machine learning model can ever give you on this data set. And not surprisingly, people have been working on this for a long, long time, back to the 60s. So this is the first thing that we know. Potentially, this could give you some way to talk about this feasibility study problem for machine learning. So second thing that we know is that if you want to take this collection of net theory and turn them into a practical system, there are actually a lot of things that you need to worry about. So the first question that we were trying to understand is given all those beautiful estimators, right? So which one is the best? How can we compare them? So if you think about this question, it's actually very hard to understand because all of them try to estimate the base error rate. However, for most of the real world data set, is actually you will never know the true base error rate. How can you compare this whole bunch of estimators without knowing the true answer? So we have amazing students, Cedric and Luca, right? Try to give us some of his their view in this paper. If you're interested, please check it out. So second question that we are curious about is that how to improve all those base error estimators. So what we actually realize is that if you take into consideration all those pre-trained feature embeddings made available, for example, in TensorFlow Hub, you can actually drastically improve the performance of many of those estimators. Given a data set, you first transform that into multiple data sets, right? And for each one of them, you do a base error estimation and you take the minimum. This actually surprisingly is a principal way for you to get a better base error estimator. So uncertainty that we know is this actually could be useful, right? So this is actually one on one data set, the x-axis is actually the runtime of system, the y-axis is the error that some machine learning model get, right? So here is state of the art, right? So, and you could run some very expensive machine learning models, right, to try to approach to the state of the art. However, if you do base error estimation, right, using some of the approach that I mentioned, right, you can actually estimate the error that you can that all those machine learning model could converge to, right, but orders of magnitude faster, right? So you can actually inject errors to make the problem a little bit harder, but as you can see, it is actually possible to provide a reasonable estimation for this very important problem. So now there are also things that we have no idea how to do, right? So one thing that we have no idea how to do is actually how to go beyond the view of base error and accuracy. What happens when your training distribution is different from your testing distribution? Whenever you have weak supervision, this could happen, and we have no idea how to model such a problem. How to go beyond accuracy, right? How can you have F1, have AOC, and also how can you deal with other utility functions, for example, robustness and fairness? There are a lot of exciting work that could happen down the road, and we are really here to actually ask for help. So another thing that, yeah, given this, right? So let's switch gear and to talk about another problem that we have been looking at. That is assuming this feasibility study step tell you, okay, your data quality is not good enough, right? What should we do? So the second question that we have been looking at is what is the most important data problem that you should fix in your training data? So here's the problem that we have been thinking about. So assuming you have a training set, it's a lot of data problems. There's a missing value, there's noise. You train a machine learning model, get a model, and then you measure some of the utilities, for example, accuracy, fairness, or robustness, right? And now it turns out, okay, it's not good enough. And we want to understand, okay, what should we do with it? If you remember Andrew's tip number 4, right? So whenever there's a bad samples in the data set, right, what is a systematic way to tell the user, okay, look at those bad examples. They could be very bad. If you want to toss them out, remove them, right? Our user don't know what machine learning really is, right? How can we enable this step as a systematic functionality inside the system? So we have been looking at two problems. The first problem is that there are a lot of data noise in the data example, right? Not all of them are equally important. If you have to clean some data example, which one should you pick to clean? And second is which training example is to blame, or which training example is the bad example for your final utility? How can we answer these two questions in a systematic way? So this is really two fundamental questions, and people have been looking at for a long, long time, right? So for the question number 1, there are a lot of research about how to measure the entropy or expectation, right? And also there's some gradient-based method. For example, there's a very cute paper called Active Clean, try to really figure out which example to clean, right? So, and then for the second question about the data importance or data influence, right? So there's a whole bunch of work about how to do Shapley value, how to expect the marginal improvement, right? And also you want to take a gradient-based view, how to do inference functions. So based on all those great work, so we have a little bit of problem of applying them to real-world applications. So the problem is that if you look at a real-world machine learning pipeline, they actually do not look like this. Instead, they look like something like this. If you think about what the whole thing is, there's actually only very small components that the user is actually trying to train a model, and the majority of the program is about data processing. It's actually a data transformation pipeline on the features. If you want to reason about what is a bad example, you have to reason about it in a joint way. You need to reason about these two things together. This is actually when we realize that we have no idea how to do that. We are lacking a fundamental understanding of how to connect two different communities. So that the data management people, the data people, try to understand how to talk about those pipelines for decades. And on the other hand, on the machine learning community, we have been thinking about how to reason about data in Python for machine learning for the last decade. However, some studies need to put these two things together in order to analyze an end-to-end machine learning pipeline. So we have no idea what's the answer, but we have been trying to do a little bit of work to understand a pipeline that looks like this. Essentially, you have a feature extraction pipeline in the middle, and we try to understand these two questions. And the thing that we want to understand is how can we compute these fundamental quantities as fast as possible. Again, let me tell you what we know and also tell you about what we know that we don't know. So what do we know? The first thing that we know is analyzing this pipeline is very hard, especially if you want to compute those fundamental quantities, for example, entropy, right, or Shapley value. However, if you look at a proxy pipeline with giving a whole bunch of heuristics, if you approximate your noise model into a cell-dependent model, if you approximate your feature extraction pipeline by only keeping the provenance, right? So here I use a very weird term called positive relational algebra query. You can think about that as your good old select from where query, right? Like use this kind of data provenance to describe this feature extraction pipeline. And if you approximate the machine learning training process as a simpler classifier, for example, k-nearest neighbor classifier, you get a proxy pipeline. And then we can actually have a p-time algorithm for many of the fundamental quantities for this proxy pipeline. That's one thing that we know. And for different shape of the feature extraction pipeline, you actually have different complexities. So, and second thing that we know is by using these fundamental quantities computed on this proxy pipeline, it actually can be useful and often work well in many, many scenarios. So this is actually one application scenario that we have. So assuming you have a data set with a lot of wrong labels on your example, right? So, and then you train a machine learning model over it. And the question we want to understand is how can we find out those training examples with the wrong label, right? So in this case, the high-level idea is if you look at the Shapley value of those examples with very small Shapley value, often negative Shapley value, should be the candidate that you should look at. And if you look at the proxy pipelines, and often we can actually give you an n-log n algorithm to compute exactly the Shapley value, which can actually return the Shapley value for all those examples in less than 1 second for a reasonable data set. And this can actually give you a very powerful way to do data debugging. So here the x-axis is how many data example the human manually inspect to fix a label, right? If you do random strategy, right, your accuracy is getting better and better, which is great. But if you really go through those examples by following the Shapley value, right, you can actually do that, have an increase of accuracy much, much faster. So third thing that we know is actually, we also know that there are application scenarios by looking at this proxy pipeline where it actually doesn't work well. So let me give you one example. So this is actually one example about fairness. So you have two different populations. One of them is underrepresented, right? So here the problem is, can we identify those already represented examples such that we can remove them and rebalance my data set? So here the high-level idea could be if you look at those examples with very small Shapley value, right? So highly likely they are those overrepresented examples. So this is actually one of the case where the idea of using Shapley value actually works really well. However, our proxy model, which actually uses a k-nearest neighbor classifier, actually breaks. So this actually goes to one thing that we are very excited about because we have no idea how to answer the question is what is the right way to really talk about a machine learning pipeline. So we all know, right? So on the upper part, that's a real realistic machine learning pipeline, very hard to analyze. We focus on this proxy. We know the right answer is in the middle, but we have no idea what that thing is. So second thing that we actually have no idea about is here we insist that to compute these four fundamental quantities because I still believe it is the right thing to do. The question is, what is the right way to actually approximate those fundamental quantities, and how can we go beyond this sensitivity style metrics? How can we measure different group effect? That's also another thing I have no idea how to do. So this is actually the two examples that I'm talking about today, right? So this is just a very small picture of this end-to-end process. If you look at many of those components, they are actually asking a data-centric problem. Okay, so that's all I have for today. Thank you for your attention, right? So if you are interested in our project, you can actually go to this two website, right? To like about details. Yeah, so I'm now ready to answer whatever question you might have. Thank you.
Thank you so much for that wonderful presentation, C. And also, you tied it back very well to the Andrew's 5 tips, and then expanded and elaborated on them and spoke about other things. So that was really wonderful. Learned a lot there. Great. We have some polls coming up, but in the meantime, you mentioned a lot about like Shapley values. For our users attendees who might be new to that concept, could you elaborate a little bit on like how those were calculated or what the concept is there?
Oh yeah, so Shapley value is a concept have a very solid game theory foundation, right? So essentially, like the calculation is actually interesting. You have n different data examples, right? So you want to say, okay, what is the importance? What is the value of one of data example? So the thing you are going to do is consider all the combinations of the rest of the data set. For example, you have 2 to the n minus 1 number of possible world, and then for each one of them, you add back the example that you want to value. You compute the improvement on that possible world, and you aggregate them in a certain way, right? So I think like later James is going to talk about data sharply, right? So like he has done amazing work there to really try to initiate the effort of using sharply value to do some of the data important work, right? Yeah.
Amazing. Thank you so much. Another concept you brought up a lot was, like Bayes error, and talked about that and how it's, hard to calculate. And you had a paper on that. So I've seen it generally, even when Andrew's like machine learning book, it's like, you use human performance and a lot of multi annotators or, human performance across annotators as a proxy for the Bayes error. So could you tell us like a sneak peek? I know you alluded to it about like about your paper and, how it goes beyond that, I guess.
Oh yeah. So there are multiple things, right? So first one is how to estimate the Bayes error, right? So the second one is how to evaluate Bayes error estimators, right? When you don't really know the true answer, right? So like again, if you have a data set, right? So if you have a one Bayes error, right, which is very close to 0, right? So how to evaluate it is actually pretty hard. So we have one paper about how to do the evaluation there, right? So and the second is given that we know which estimator perform well, how can we use that to build a system to do feasibility study, right? Yeah.
That makes sense. Thank you so much for elaborating on that. Next question we have from John. He asks, are you aware of machine learning interfaces that incorporate Shapley values to alert users to address data quality issues?
So that's a very good question. So it depends on how large scale that you're talking about. So personally, I don't know any large scale deployment of Shapley value today, right? So I know people have been thinking about it for a while, and I have talking to many cloud service providers. Maybe in the near future, they are going to have the Shapley value maybe for the training set, but also Sharp for the feature expandability part. So far, maybe I don't know, but probably I'm wrong. Yeah.
Maybe we'll see a bunch popping up after your talk since they watch this. So, we have another question from Seth. He says, is it correct to say that you advocate rebalancing the training data by removing some examples from classes which are overrepresented?
No, I mean, I don't advocate that, right? So, I mean, I'm not an expert in fairness, right? So that's just
Right.
one example we constructed that we know our approach doesn't work. Whether it's a good way to deal with fairness or not, I'm not the expert. Yeah.
Makes sense. Thank you. Lastly, we have a question from Labe saying, just nice talk. Any comment on research papers addressing label noise like divide mix?
Oh yeah. So they are fascinating, right? So there are different ways that you can actually measure, like try to deal with label noise, right? So I think like Snorkel is fascinating there, right? So like you can actually use different type of signals to help you to fix the label noise, right? So even doing that automatically, right? So there are different ways, right? So we are not trying to replace them, right? So we are actually trying to say, yeah, maybe at some point human can become one of the signal. If you know you have the human time for 1 hour, right? So which component should you focus on such that you can make those automatic approach even better, right? So that is actually our thoughts on this. Another thing is we could use those automatic way of label, like fixing label noise as our candidates, right? For example, we run all of those tools and we get the candidate label, right? And then maybe we can compute some metrics such as entropy to tell us, if you have a human to look at them, this is the place to look at them, right? So that is our hope. And again, we have no idea how to answer that question, but yeah, we have been looking at that for a while. Yeah.
Makes sense. Thank you so much again for the wonderful presentation and for taking the time to answer the audience questions. It was a pleasure having you.
Yeah, thank you so much.